Okay, good afternoon. So we're going to pick up where we left off, talking about statistics probability distributions. We had been working on basically what was a nice introduction to what a probability distribution is about. And we were looking at the sum of two six-sided dice. What is the distribution of the different outcomes that are possible, 2 through 12. We saw it had a nice little shape. It was symmetric. Calculations, we started to talk about what the point of it was, that although you lose some of the precision of, say, the table or list of outcomes, you gain something specific in terms of being able to look across the entire event of rolling two dice and looking at their sum. So what we're going to do today is actually just complicate that a little bit. So we're going to look at the sum of three six-sided dice. So we want to get ourselves into thinking about it. So remember what the dice look like. They're cubes. Perfectly weighted in this theoretical sense. While we're learning right here, we're talking about perfectly weighted dice. So they have these six sides. Each face has one of these six numbers. Each of them is on there once, and each is equally likely to be the face-up side. So what we're imagining is rolling a dice and seeing how it lands, what faces upright. So if it's 3, then we're saying that's a 3. And so if you roll 2 and you get a 3 and a 4, you get 7. And if you roll a third one, you get a 5. That's a total of 12. So we want to think about this. So times 3 in the colloquial sense. Obviously, we're not just multiplying things. But we want to think about, first of all, what are possible sums? And if we can give ourselves a range, that'd be very useful. So remember, rolling two six-sided dice kind of get us into this thought process of what are the boundaries here for this theoretical experience. Well, it was 2 to 12, because with the 2 you get 2 1s, and with the 12 you get 2 6s, the largest on any individual dice. That's going to follow here, 3 to 18. It's difficult to make the two-way table with 3 dice. It's difficult to make the two-way table with 3 dice. And in fact, we might run into a situation here where we're having difficulty counting altogether. Why is that? Well, if you remember, the 6 by 6 table yields 36 possible sums. So that's tricky now, because what we're talking about here is those 36 possible sums. Cross that with the probabilities on the next one, right? So we should think about this for a second. So we might find that this strategy doesn't quite work out, but let's just look at it. So there's a way to get a sum of 3. Okay. There's a way to get a sum of 4. But there's another way to get a sum of 4. And indeed a third way to get the sum of 4. So we've already seen this sort of explosion here. There's something going on. Okay. We think about the 5. We could get 1, 2, 2. You get 2, 1, 2. You get 2, 2, 1. But we can also get 1, 1, 3. 1, 3, 1. And 3, 1, 1. So we're kind of very rapidly expanding sort of the difficulty of counting here. And in particular, you know, this is not systematic enough for us to, for me at least, to feel confident that I've remembered or kind of isolated all the potential ways of getting a 5. And so you might start to think, like, what are the strategies that we can do here? Well, one big one, of course, is to stay organized and make a table, like we're doing now. There are theoretical ways as well to do this. So what we want to think about to some extent, or what we can think about to some extent, is 2 dice in isolation, making this table of 2 to 12s. And then the third dice interacting with those potentialities, right? So let's put that a different way. Dice 1 plus dice 2 is 1, 1, or a sum of 2, 1/36 of the time. So that means that kind of in isolation, we can think about now, well, then what are the distributions of the sum when we roll this third dice, right? So 1/36 of the time, we get a 2 as the sum. And then we have 6 branches for the third dice. 1, 2, 3, 4, 5, or 6, which cause a sum of 3, 4, 5, 6, 7, and 8, respectively. So we get this kind of neat relationship here where we start to think about, and right now I'm trying to have us expand our thinking about probability here and what exactly is going on. So the tools are useful, but let's make sure we get the concept solidly. So what we're saying here is essentially twofold. We're saying 2 things. One is that the dice 1 and 2 are independent from the dice 3. Now the sum is not independent, but the dice are independent. So we can, in some sense, kind of deal with them separately or in separate combination. We are also acknowledging, very importantly, that different outcomes for the first 2 dice occur at different probabilities. So let's just, for example, compare 2 and 3. Now 3 has, with 2 dice, has 2 ways of getting it, a 1 and a 2 and a 2 and a 1. Now after you've established that, you get this same distribution of potential dice 3 numbers. So this type of distribution for the sum. Hopefully you're starting to recognize maybe some patterns, what we're talking about. Hopefully you also recognize that this is a bit more systematic of a way to think about this, right? This tree diagram is really illustrating something a bit differently than the 2 by 2 or the 2 sided table, right? So we are able in some way to go about this very systematically. We know what the potential outcomes of the 2 dice are. So we can start to think about here what our potential outcomes are for 3 dice. The tree diagram is very useful, right? Because what we want to be careful with is that there is an issue with trying to do it as a two-way table and saying, well, let me just list the outcome possibilities for sums of 2 dice, so on to 12, and then list the outcome possibilities for these, for the third dice, and then just write them in. What is the issue? What is the issue? And we can fill this out. Now the issue here is that the left-hand column, these are not equally likely situations, right? It's not accounting for this. So we want to be able to sophisticatedly say that it matters a great deal if outcomes aren't equally likely. It matters a great deal for the calculation of it all, right? That these highlighted things are very important because there's a chance that we start to see all of these parentheses sets as equally likely. They're not. This is how things are very different in this case, to analyze in this way. There is a way to do this that does make it equally likely, and it's that at first you make 6 branches, and then 6 branches off of that, and then 6 more branches off of that, and then they're all equally likely. That's not exactly what I'm doing here. What I'm saying is that I'm not making equally weighted branches. I'm saying the branch to 2 is only happens once out of 36. The branch to 3 happens twice out of 36. So that means that this 4, the way that 4 happens, is twice as likely as this 4. And we can see this. Let's look back at our 4s. The 4 with which the first 2 dice are 1 only happens once. The 4 with which the first 2 dice are not 1 happens twice. The first 2 dice sum to 2 and then you get a 2, or the first 2 dice sum to 3, but that happens twice, and then a 1. So what this is really getting at is the remarkable importance of counting in statistics, right? At its core, one could argue that probability is a method of, it is sophisticated counting, right? It is attempting to count cases, to analyze each one, to say we've looked at all of them, and to say we understand each individually so that we can look across them. It's a very difficult thing, and it often develops with statistics into tools that estimate, that don't quite get it perfect, but they estimate well. Right now we're still in theoretical probabilities. We're not quite there. So this is perfect in the sense that we get to set it as so in order to learn. Okay. Let's look at the 5s for a second. Let's say we had that right. We notice is that there are 6 5s, right? But this one is relatively rarer. Now, where is that one? It's right here. how much relatively rare is it? Oh, sorry. Well, it only happens once out of the 6. The one where the first 2 dice sum to 3 happens twice, and where it sums to 4 happens 3 times. Right? How can we see that? Well, this one happens once. No surprise that that's a 1. This one happens twice. No surprise that's a 2. This one happens 3 times. No surprise that's a 3. So we start to see this multiplicative effect happening. We can look at essentially the likelihood overall out of all of the outcomes possible here is going to be oops, sorry about that. Multiplying across the individual probabilities. So here we start to talk about this 3 out of 216, 2 out of 216, 1 out of 216. Overall, the odds of getting a 5, a sum of a 5 on 3 6-sided dice, is 6 out of 216 different combinations. Here they are. Now, it's no secret here that there's no perfect sort of way to do this quickly. Even the 2x2, even the 2 6-sided dice table was really a decent amount of work. I mean, we're establishing 30, we might have seen the pattern, so it was quick. We're establishing 36 outcomes. Each outcome was equally likely, but as a sum, the outcomes are definitely not equally likely, right? A 7 is more likely than a 2 or a 12, or more likely than any other thing individually. So, but this is getting us very close to thinking about some very, very important ideas, including independence and the multiplication of probabilities. Now, of course, it gets pretty messy here. Messier than we can really do in this particular format very well. Suffice it to say that a similar type of pattern emerges. Right, in the sense that getting some of the middle sums between 3 and 18 are more likely. Now this is a not perfect thing to be looking at, because this connected line is giving us a sense of continuity that isn't actually there. There's a discreteness to this all. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, nothing in between, nothing outside of those things. But we want to start thinking about that shape very, very critically. Okay. So here's a generic look at sort of what we're talking about here. This is what's happening. Right. And we get, this is obviously a sketch on purpose, and it may not be even accurate, but we get this sort of same shaping that we got for the sum of 2 6-sided dice, right? And this is what we want to start extrapolating upon here, which is to say, okay, so we have 16 possible outcomes instead of 10 or 11. we understand the discreteness of it. But if we were to add a fourth dice into the mix and look at sums, it'd still be this shape, right? There's a theoretical side to this where these inner numbers, they're more likely of happening because there's more combinations that yield them. And so this leads us to a particular shape with this type of symmetry and peaking. And we're, well, where do I want to leave you thinking? I would like us to think about the idea that, first, actually, yes, continuity is probably the best. So continuous, right? So right now we've been talking about discrete probabilities. Now, what does discrete probability really mean? Essentially, it means that you have this finite countable number of outcomes, right, with non-zero probabilities. So you have this non-zero, like, you can only count the number of ways that a dice can come up, right? There's 6 right there. And even if you start thinking about thousands and thousands of dice, it's not infinite. You can count it, you can bound it, you can count it. There's only finite numbers of non-zeros. Not everything is like that. And I think the easiest real life analog to this is things that have to do with time. Things that have to do with time. And let's leave then with this scenario rattling around for a while. Light bulbs. Okay. So say you are the supplier, the logistics manager for a large building. Okay, large building, you think of like a commercial office building. So generally the lights on the ceiling are the same type of lights. They use the same type of bulbs, done on purpose to make it consistent, to make it easy. But you have to wonder about this question. If you install all the bulbs in the new lights, new bulbs, plug them in, all of them are off. You turn on all the switches at the same time, they all go on. You just leave them on in this hypothetical situation. You ask yourself this question: will they all burn out at the same time? Now, possibly, but insanely unlikely, right? In this sense, there is a range of lifespan of the light bulb. Some of them, just via their nature of how they're constructed, maybe they have a different percentage of certain metal in them, in the coil. Who knows? I don't know. But they don't all stop working at the same time. There is a distribution to them. Now think then in this theoretical space, any particular light bulb, what is its likelihood of lasting a certain amount of time, right? The likelihood of lasting for 3 months, 10 months. Think about this connected idea. What is the likelihood of it dying at any particular time? 1 month, 10 months, 100 months. Maybe eventually it's 0. But in between there with time, we want to recognize that time is continuous, so we don't think about it in, well, actually, let me say, we do think about it frequently in discrete terms where we break time into seconds, say, or even minutes. But those can be subdivided further and further infinitely on. And so we get what are essentially continuous probabilities, right? I don't have offhand what the shape of the light bulb burning out is. It's probably normal. But it is continuous when we think about time. And probabilities, right? So that's where I'll leave you today. Next week, we'll probably look at continuous distributions a bit more. Until then,